Hello, good people. Welcome to this is kind of the bridge video that's going to take us from infinite series that we've been doing with values to infinite series that we're going to look at that now involve variables. So this is the last part of Unit 10. And I wanted to, create this video to bridge, both sides using things that we've learned in the first part of Unit 10 with all those limit tests, and then applying them to new situations where we're going to have some variables involved. Just as an example. So here's something that at the beginning, this might look like a very innocuous expression, right? 1 over 1 plus x squared. Have we seen that before? Probably. How have we seen it before? In many contexts. But I guess I want to connect it back to this idea that this setup reminds me of this setup. And I should say A1, 1 minus R. So now, going back in time, what is this? Well, this is the formula to find the sum of a geometric series. The geometric series is the only type of series for which we can actually find the sum, and this formula helps us do that. But when I look at this initial expression, it kind of follows that pattern. And so what do I know? Well, I know that in this geometric series, my a value, my a sub 1 value, the first term, is actually 1. How do I know that? Because this goes with that. But now to figure out the ratio, now remember, normally the ratio is the number that we keep multiplying continuously in order to get the next term in the sequence of numbers that I'm adding. But in this case, my ratio is not a number, it's a term. This is the term that I keep multiplying by every time in order to get to the next term in the sequence, right? And so when I look at this, if I think of this denominator as 1 over 1 minus parentheses negative x squared, I have my ratio. This would be this. Just for consistency's sake, let's use this version of my original. So this is the original. If I rewrite it just a little bit, I can say, oh, adding is the same thing as subtracting a negative. But when I do that, I create a pattern that looks like the sum formula of a geometric series. If that's the case, then I know the first term is 1. And I also now know that my ratio is negative x squared. What does that mean? Well, that means that I can build a sigma starting from 1. Actually, I think we're going to start from 0, and I'll tell you why in a little bit. And going to infinity. So this is an infinite series because geometric series, we've been studying infinite geometric series. The first term is 1 times the ratio, which in this case is negative x squared, to the power of n. And maybe I'll do this 1 in the color that I originally circled. Now let's double check and make sure that we're on the right track. From this setup, which we converted into a sum formula for a geometric, not SOME, but SUM, sum formula of a geometric series, of an infinite geometric series, we gathered that the top number is the first term, and then what I'm subtracting, which is negative x squared, is my ratio. That's the thing that I'm multiplying every time to get to the next term of the sequence. Using that, I created this sigma. So I'm saying that this sigma is equivalent to this. Now, what does this sigma look like? We're about to expand this series. But let's just double check. Why did I choose 0? Well, if I substitute 0 into my n, negative x squared to the 0 is going to be 1 times 1 gives me my first term as 1. Now, if I had selected 1 here, and I can select 1 here, then I'm going to have to subtract 1 here in order to get the initial term to be 1. So I could do it either way. I could leave it as 1, n minus 1, or I can just say, oh, it starts at 0, and then just take this away. Both are equivalent. Both are giving me the same series. Now, what does the series actually look like? Well, let's see. If I substitute 0, that's going to be 1 times 1. My first term is 1. When I substitute n equals 1, that'll be negative x squared negative x squared to the power of 1, which is negative x squared, times 1. So I'm going to get plus negative x squared plus. If I substitute 2, well, I'm going to square negative x squared. So that's going to be a positive x to the fourth times 1. So that's positive x to the fourth. Is it okay if I don't multiply by 1 and I just worry about this piece? Because if I multiply by 1, it's going to be the same thing. Substitute a 3, negative x squared to the third power. Well, negative to the third power is going to produce a negative, and x to the second to the third is x to the sixth. Now, at this point, I notice, hey, every other one is going to be a different sign, right? 1 is positive, x squared is negative, x to the fourth is positive, x to the sixth is negative. I'm also noticing a pattern with the exponents, but I'm going to continue going. What if I substitute a 4? Then negative x to the second to the fourth power is going to be x to the eighth, and so on and so forth. Negative x to the 10th plus, and if you want, you can do this, right? To show that we're really, and I'm just going to say, and it goes on forever. Now, some people say, well, I don't want to put a plus and negative. Why don't I just say 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth minus x to the 10th. This series that I'm creating is what we're going to call a power series. And that's going to be the first set of videos with the notes pages you got today. Is we're going to talk about power series as a way of expressing this never-ending sum that involves powers of a variable, usually powers of x. So this is a power series because it involves powers of x, not regular numbered terms, right? They're not numerical values. But what we just created was we expanded this series from sigma, but the sigma I created from that. So therefore, I can say that 1 over 1 plus x squared is equal to 1 minus this never-ending list of terms or powers of x in this pattern that I'm writing out. Plus dot dot dot. Yes? Does this actually work? Oh, wait a minute. Remember geometric series? Geometric series were only convergent if something happened. Specifically, they were only convergent, so only converges if dot dot dot. When did they converge? Oh, when the absolute value of r was less than 1. In other words, when the absolute value of negative x squared is less than 1, which is to say the absolute value of x squared is less than 1. So when does this happen? What kind of x values would make this statement true? Can I plug in 3? Well, no. 3 squared is going to be 9. Absolute value of 9 is not less than 1. Can I plug in 1? Well, no, because 1 squared is 1. Absolute value of 1 is 1, and 1 is not less than 1. But anything less than 1 could work. Do I stop at 0? 0 squared is 0. Absolute value of 0 is 0, and 0 is less than 1. But what if I put like negative 1/2? Negative 1/2 squared is positive 1/4. Absolute value is positive 1/4, and that's less than 1. So really, this is what we call the interval of convergence. I'm going to write this down. In this interval, that's where I am assured that my series converges. Why? Well, because of the geometric series conditions where the absolute value of the ratio had to be less than 1, then that means that in this window, my series is going to converge. So coming back to where we ended here, the question is this true? Yes, but only for those x values. How do we know that that's the case? Well, Let's pull out our calculator and we can see some things. Why don't we check it? Why don't we pick a value in that window? So let's say at x equals 1 half. 1 half is between negative 1 and positive 1, right? So at negative 1 half, what is 1 over 1 plus 1 half squared? What is that? Well, if you do it by hand, this will be 1/4. 1/4 plus 1, that's going to be 5/4. And if you do that, 1 over 5/4 is the same thing as 4/5. I think that would be 0.8. If you don't believe me, grab your calculator and we can do this fairly quickly. 1 plus 1 over 2 squared. Oh, that's not the square. Squared. And we get 4/5. Hey, that's what we said. Great. So how do I know that this is going to work? Well, I'm going to have to substitute 1 half. But here's the problem. We said that this series is equal to that original function expression, but if it's an infinite series, do I have an infinite amount of time to plug in 1 half wherever I see an x? I don't, so I'm going to approximate. So we're going to say this is approximately 1 minus 1 half squared plus 1 half to the fourth minus 1 half to the sixth. And let's just go out to eighth here. Plus 1 half to the eighth. I'm going to stop here. So that I didn't include everything, right? So I chopped it off and I only used the first 1, 2, 3, 4, 5 terms. So therefore, this is an approximation. But what I'm banking on is even just using these first 5 terms, I'm going to get an approximation that is going to approximate 4/5, which is 0.8. Let's see. Go to my calculator. 1 minus parentheses 1 half to the power of 2. Oh, to the power of 2. Added on to parentheses 1 half to the power of 4 minus. And all I'm doing is I'm substituting 1 half into my sequence, but I'm only going to use the first 5 terms. I can't use all terms because we don't have that amount of time to just add an infinite number of terms, but I can at least add the first 5 terms. And when I say add, I'm saying this is a negative term, so I'm adding it. I'm really subtracting it. So this setup that I have here, that's what I just put into my calculator. Oh, I did not put that into my calculator. My bad. 2. So I'm substituting 1 half wherever I see an x. I press enter, and I get this number. And you're like, well, what the heck is that number? I don't know. What is 205 divided by 256? And my answer is, hey, pretty accurate. 0.80078, right? So this is about 0.80078. This is the actual answer. This is my estimate. And if I round to 3 decimal places, it's exactly the same. That's a pretty good estimate. So what we're going to find is that sometimes we can make functions have equivalent power series, so that whatever I need to substitute into the function, I can substitute into the power series, and I'm going to get a pretty good approximation. Now, if I were able to put an infinite number of terms and add them all together, I would get the exact value of the function. And that is what this second part is about. We're going to take complicated functions like exponentials, like trigonometric, like natural log, and we're going to find a power series that is equivalent to them. And here's why. On this side, I have a rational function. Rational functions come with their own set of problems, right? They're sometimes discontinuous, sometimes they have holes in them in the graph, sometimes they have vertical asymptotes. But over here on the other side, I have this never-ending polynomial. And polynomials are always nice because they're always continuous. They're always differentiable. They're always integrable. And so if I can create a never-ending sum of terms that is a never-ending polynomial to equal a function that causes problems, I'd rather use a nice polynomial than that. Not only that, but as you saw, just by using the first 5 terms, we got a pretty good estimate to the actual value of the function. And spoiler alert, that's how your calculator is programmed. It doesn't really do e to the 2 power. It does a power series and estimates it like this. And we're going to be able to do that in the next set of videos that we're about to do. So, big idea. We're going to use ideas that we discovered when we were doing numeric infinite series, but we're going to apply them to power series. Power series are infinite series that involve powers of x or powers of a variable. And we're going to find that sometimes we can create a power series that is the same thing as a given function. And as we saw here, we can get a pretty good estimate. That's where we're going. And so as we start the next set of videos, we're going to get into power series in general. And then we're going to do something magical, which if you haven't thought about it, it's going to make your eyes go really, really big because you're going to realize, oh, that's what we were doing all along. And we're going to start Taylor polynomials. Okay, well, pause this video. We're going to start power series in the next video.